Hello everyone, I'm Sadia and today I'm going to give a lecture on Opensees, which includes definition of Opensees, Truss example, code details, beam transient or dynamic analysis, its results, and then conclusion, and I'm going to give a small assignment as well. What is Opensees? It's an abbreviation of Open System for Earthquake Engineering Simulation. It's an open source software framework for developing sequential, parallel, and grid-enabled finite element applications in earthquake engineering. Well, actually, this OpenSees uses a tool named as finite element method in order to analyze structures by dividing the structures into small elements, finite elements. You can see these finite elements. This is whole structure, which is divided into finite elements. By knowing the response of this small segment, we can sum up the response of all of the segments and we can get the response of the structure no matter what the shape of the structure is. Therefore, this is a very useful tool to get to know the response of irregular shapes or any complex structure. I'm going to start with plain truss example as a basic example to know the coding and language of Opensees. How does they use the commands? This is two element truss example with 3 nodes, and these are the element members, and we are going to apply 12,000 force down direction at node 2. First of all, I'm going to just give you a basic idea of FEM equations, how we can solve it manually. So this is the manual example. So starting with the global stiffness matrix, it's going to be the combination of element stiffness matrix and using the force F is equals to K into U, the stiffness into displacement, Hooke's law, a formula, we can find the displacements. But before that, we need to apply some boundary conditions. So here we applied boundary conditions corresponding to these forces. We are just left with U2 and V2 that are the displacement in horizontal and vertical direction at node 2. So we were left with this equation, these two equations, and out of them we have extracted 0.57 millimeter in horizontal direction and 1.96 millimeter in vertical direction. Now we are going to use Opensees to solve this example. Here we can see the input of libraries, then coordinates, and wipe command, model builder, nodes, constraints, developing the elements, and then defining time series, etc. Here we have defined recorders and then analysis steps, which are going to be used for almost all analysis, and then printing the displacement. It's a simple example, and this is the result, which was almost same as that we have got in the previous slide, like 0.57 and 1.96, and we have got 0.57 and 1.9, almost 6. So here what we did, we imported the libraries which were necessary for the implementation of all of this code. We use Opensees because mostly all of the commands are from this library, and we use NumPy because numerical calculations are based on this library, which has a function for working on domains of linear algebra, Fourier transformation, etc. We have this PyPlot from Matplotlib, which is going to help us create the figures and create the areas for the figures, etc. And this open post-processing and rendering is for plotting the model. At the end, if you wanted to just plot the model, whatever that we have fed to the model, elements, coordinates, etc., I wanted to see how does it look like. This is going to help us. Here we start with the input variables. Here are these coordinates, and then area, elastic modulus, load in x direction, y direction. Here we're going to define the materials, how Opensees use the material commands. It can be uniaxial based on the deformation, divided into different types. We mostly use uniaxial, which consists of steel, concrete, elastic, So we use elastic uniaxial material. Here we have used it. Now starting with the model command, we need to wipe all of the existing models. So this command do wiping process, and then we need to define the model, which is basic, and we have this number of dimensions. We have 2D, and then number of degree of freedoms. We have 2. Uniaxial material used here as elastic material because it's truss, and tag of the material property is 1, and elastic model is E with E command, which we have already defined. So basic steps for leading toward analysis are the model builder that we have just defined as model, and then domain, which consists of time series and recorders, and then analysis. Domain has elements, nodes, multi-point constraint, single point constraint, load pattern, time series. Elements have truss, can be truss, like we are using truss, so we are going to define it as truss. And if we are going to use a beam, we can define it as elastic beam column or force beam column, which can be considered as non-linear. So we have here we have defined nodes, boundary conditions, and elements in time series. Nodes are defined like node. Then we are going to give the tag of the node and x coordinate, y coordinate here. This one is x, y. And likewise, we are going to fix the first point node and the third node. So as it is having fixed boundary conditions, and then it has single point constraint. So defining elements, here it is truss, and element tag is 1, and it is from one node to second node, and its area is 1, and it is using material property as 1. Time series, we are going to use linear. So what is linear? A time series that can be modeled as a linear autoregressive, like I'm going to explain later as well for load control command. What is autoregressive? It's when the model predicts future behavior based on past behavior. Like if we have time 1, t1, then we want to know the time 2, t2, then that is termed as autoregressive model. So defining the load pattern here we take plain load pattern because we just going to take some gravity loads or nodal loads, and giving the tag to this pattern so that it can be used for load or etc., anything where it requires, and then giving the tag of time series as 1. And then we are going to define the load, which is going to be at node 2. Px load was 0 and py was minus 12,000. So recorders are here in Opensees. Recorders can be element recorder, nodal recorder, envelope recorders, etc. And these recorders for the renderer are based on the library that we have imported in the last post-processing renderer. And this whole data can be shifted to cloud computing system, for example, MySQL, etc. The command for load recorders is as following, which consists of recorders as if you wanted to record the output on nodes, so you're going to define it as node, and then you want to save it in a file, then you have to define it as file as node displacement dot out. And this time is going to close the file after every step and then reopens it. Whenever that you are going to run the analysis, it's going to close it, open it, and then close it. Then you define the node where you wanted to see the deflection. Then you define the degree of freedoms in x and y direction, and you give the name, the what do you want from that node. For example, displacement. Likewise, you go for reactions and forces. Forces are found on elements, not on nodes. So we see that what force are here on elements. There are other recorders as well. You can define anything that you want to extract. Then we come up to defining some analysis steps, like what system of equations that you are going to use is band SPD. The band SPD is symmetric positive definite. It handles how equations are stored. And then we are going to define OP, numberer, RCM. I have defined in another slide, the next one. but it's just to give the numbers to the system of equation. Basically, system of equations are going to reflect degree of freedom, so it's going to just give numbers. RCM system, number is used here, and the constraints used here are plain. Like I have defined earlier, the plain constraint is single point constraint, and single point constraint is a homogeneous degree of freedom that, for example, we have fixed degree of freedom on both ends, like one or more degree of freedom are fixed for a given node. In our case, our node 1 and node 3 was fixed, therefore it has homogeneous boundary condition, and therefore it is termed as single point constraint. Okay, this is defining this one. Analysis steps includes static analysis or transient analysis. We have constraint handlers, which are further divided like this. When we want to use them, we're going to use a transformation or Lagrange. Here we have used this number as RCM, an analysis model, solution algorithms. We have used here linear, but we can use Newton, Ramson, or modified Newton, like we are going to use in Beam. An integrator can be static, an integrator, or transient. Here we have used static, and load control could be displacement control as well. System of equation, we have used band SPD. Again, the RCM is going to give the numbers. So analysis steps are the commands used here. Integrator, load control, algorithm is linear. This is going to give the iterations, how many times you're going to integrate. Algorithms is linear, analysis is static, initialize the analysis and then analyze it in one go. Here we are going to save the displacement as OP node displacement at second node in y direction, and then second node in x direction, in x direction and in y direction here. And this is how we are going to display it, and this is how we are going to plot the results. So again, details of LC on the next slide. Load control details are on the next slide as well. Okay, these are the results, and this is the plot. What is load control integrator? Like we have seen, it requires a command as load controller and in the iterations, number of iterations, right? We just took those. We didn't consider lambda because we let the load controller decide what the lambda it is going to use. So here, p naught, suppose we are applying p naught to our beam column, then we need to have a time series, which is going to increase with some step. For that, we need to know the time in T2, and T2 is basically equals to lambda delta T plus T1, and if we consider delta D as constant, then T2 depends on lambda and T1, and this load controller is going to find out the lambda value, and we are going to put it constant, and then if it is constant, then we have linearly increasing time series, which is going to affect the force applied, because the force will also change by the constant factor like this. So we are going to get a curve, and it will work till the top, till the peak, but it's not going to construct this the deterioration curve. But anyhow, we usually do not much require consideration of deterioration curve, therefore load control can be used in our analysis. So I'm going to stop here, and I'm going to make another video for the second beam analysis. Thank you very much.